All right, folks, welcome back. We wrapped up talking about the Gram-Schmidt process and how it relates to the QR factorization of a matrix last time. And I teased at the end of the last video this page where we talk about how we can kind of extend our knowledge of inner product spaces to how we might go about solving these AX equals B systems. And last time we said we could do that by using the QR factorization in a two-step process. But the real question that we want to answer first shouldn't be how to solve a system, but whether or not the system has a solution to begin with. And this proves to be of great importance, again, especially talking about differential equations as a strong candidate for this theory. But what we really need to establish is that there is a solution to our AX equals B systems before we go and start finding solutions, right? We don't want to start an algorithm and have it never terminate or not find the correct thing, or if there is a correct thing to find in the first place, it's something that we really need to hash out. And we are building toward the idea of something called the Fredholm Alternative. And the Fredholm Alternative is going to tell us exactly when we have a solution to AX equals B in an inner product space. And specifically for our purposes, this is going to happen inside the standard Euclidean space, Rm with the dot product. So, in order to get there, in order to build the machinery behind to establish why this particular theorem here is true, we need to understand a little bit more about what Gram-Schmidt was doing, and we need to talk about the idea of an orthogonal projection, and then the idea of an orthogonal complement, and then figure out why these notions are related to solving the AX equals B system, or how they're related. All right, so let's dive in here, and we're going to begin with kind of a generalization. Right, we're going to start with some subset of a vector space, V, and this is going to be inside of an inner product space. Then any vector in V, or a vector that is in V, will be said to be orthogonal to the set S. So if the inner product between V and any element of S is 0. So before, we were talking about orthogonality as a property between a pair of vectors. But what we're saying now is that we can go ahead and fix one vector and then compare that vector V against every element of some set S. And that is going to give us this notion of orthogonality to a set, as opposed to orthogonality to a single vector. So this extends that notion a tiny bit. Right? As an example, this plane here, this is pi for plane, capital Pi. This is the equation x plus y plus z equals 0, right? So there's an algebraic equation whose locus is going to tell us about a geometric object sitting in R3, and this guy is going to be a plane, right? I can solve that z equals minus x minus y. And when I do that, I can actually find that this plane is spanned by this pair of vectors, right? And effectively, this is going to be the null space of this matrix 1, 1, 1, right? And you can go ahead and verify this, right? This is a two-dimensional subspace of R3, and we can span it with these two vectors u1 and u2. Okay, so what we want to do with this is note that the vector v, which is 1, 1, 1, I picked that up off the coefficients on these x, y, and z terms, right? So the vector v is going to be orthogonal to pi here, right? And this is the idea. This is the normal vector. So the normal, or a normal vector for the plane pi. Right, and you can check if the vector v is orthogonal to both elements here, right? It's orthogonal to u1 and it's orthogonal to U2, then we can say that this guy is going to be orthogonal to both, or it's going to be orthogonal to any element, or any element in that plane, right? It's going to be orthogonal to any vector that is in that plane due to the following argument here. So we're noting that, yes, indeed, V, if I dot that with minus 1, 1, 0, so 1, 1, 1, dotted with minus 1, 1, 0, sure enough, that dot product gives me 0. Very, very similarly, I'll have 1, 1, 1 dotted against minus 1, 0, 1. That's still going to get me a 0. So this vector V is orthogonal to both elements of the basis for the plane. And since every element in the plane can be described as a linear combination of the basis vectors, and I just erased them, right? Any element in the plane can be written as a linear combination of those two vectors. I invoke the linearity on the inner product to find V inner product U1 and V inner product U2 as part of that computation. And therefore, any element W of the plane must also be orthogonal to V. So V is orthogonal to the plane pi, right? So this would be an example of how we're extending this notion of orthogonality to sets rather than just single vectors. Okay, so more generally, if V is perpendicular to an entire basis of some subspace W, then V is orthogonal to the entire subspace, right? So if I can just go ahead and establish orthogonality to a spanning set in particular, then I've shown that V is perpendicular to every element of that subspace. So I don't have to go and do this in general because I can just show it on a basis and I'm done. But that's only if I'm dealing with a subspace, something that is closed under linear combinations. Okay, so do be very careful with that statement. Now, we've established this idea of being orthogonal to a set. So now I can tell you about an orthogonal projection, right? An orthogonal projection, you can follow this definition for sure. It's no problem. It's really no problem. It's just a rigorous statement of saying that every pair of vectors casts a shadow on one another, right? So V in this picture is casting a shadow on the subspace that is spanned by S. And in particular, it's doing so in an orthogonal fashion. So the sun is way up here. I should do that in yellow because I have the pen for it. And this is going to be a bright yellow. Oh, where's my color wheel? More colors. I want yellow. There we go. I'll put you right there. Apply. Awesome. Here's my sun right up here. All in its bright shining glory. Okay, and the sun is going to cast a shadow down on V, or it's going to shine on V, and V will cast a shadow on this subspace that is spanned by S, or the vectors in S. Right, so that's what this picture is saying, is that we will get this shadow vector right here, and we're going to call that the orthogonal projection of V onto S. Let's see if I can clear that picture now. Whew, awesome. Okay, so really, this is the guy that we're looking for. This is the projection of V onto S. So proj sub S of V. If you want to think about this as a function, you should, because it is a function. Right, and we're actually going to show that in the next proposition here, that this is a function, that there's only one way to cast a shadow in an orthogonal fashion. So there is but one orthogonal projection of a vector onto the set S, which is a subset of their containing inner product space V. So the proof here goes to say that, let's suppose that we actually had two different projections. For some reason, let's say we had two different projections of this vector onto the set S, and we'll call those two projections X and Y. Then we know off of this picture here, right? If we say that this guy, this is X, x is v minus s, right? Or if I add some element, some vector s to x, I will get v, right? And the same goes for y. There's going to be a different element, s, that makes that true, right? So let's see what happens, right? I know that these two vectors, if I subtract them off of v, will produce something that is orthogonal to s. So it's really that leg of the triangle. Okay, this is all we're saying. That there is some s, or in fact, no, this is going to have to work for all s if we're in the complement, or if we're orthogonal to that set. Yeah. Then there is this relation for every s in the span of s. Okay, so we are orthogonal to everything in s. And that's important here. We need to be orthogonal to everything in that set. So I can take this equation and subtract I can subtract the v minus y inner product from the right and put it onto the left of the equation, and then invoke linearity. So in particular, look what happens. Right, if I scroll down here, v minus x inner product s minus v minus y inner product s. I invoke linearity on the first bit, so this is v with s minus x with s, and then I subtract off, what is it, v with s, angle bracket, and yeah, it'll be a minus y with s. Right, so I'm invoking linearity here. And notice, I get a cancellation in these two terms, and the thing that's left now is y minus x inner product s, where I can recombine with linearity, and that's exactly this term right here. And I know that that has to be 0 for every element in the span of s. Okay? Because y minus x is also in the span of s, this last condition means that this vector has to be the 0 vector, right? It's because I have to do this for every element in that spanning space, right? So that means that y minus x has to be the 0 vector, and therefore, this last little bit here, y would have to equal x. So there is but one orthogonal projection of a vector onto a set. Okay, so let's go to the top of the page here, and let's see, what do I want to do? Let's go ahead and stop the video after the next theorem. But the idea of this theorem is to say that if I have an orthonormal basis for a subspace W in an inner product space V, then the orthogonal projection of V onto W takes a very specific form, right? In particular, let's see, I don't like this. I'm going to go ahead and lasso this and move it over. Oh, so close. There we go. Get over here. Get back on the page. There we go. Okay. That the projection, I can actually go ahead and just, I can go ahead and take the coordinate components from our orthogonal coordinate theorem, or our orthogonal decomposition theorem, and say that each of these elements, each of these weights that I have to attach onto the UK vectors, is just what the coordinates are for W, right? And this follows from what we've done before about what these coordinate vectors have to look like. And we can check that v minus w inner product ui hat has to be 0. So indeed, v is going to be orthogonal to this w, right? Or v minus w is orthogonal to u. Okay, so yeah, that would mean that, yeah, w lives in there. Okay, yeah. So no problem. This is just from the uniqueness, this result follows from the uniqueness of orthogonal projections, right? That there's but one way to express u, or express w, in terms of this orthonormal set, or orthonormal basis for w. Therefore, if I'm going to project this this vector v onto this W space, then this is what has to be left over. And this actually, you can see this as part of Gram-Schmidt, right? If I'm taking V and trying to project it onto some space W down here, then there is this orthogonal projection, and this would be some multiple of a U, so I'll call it U1 without the hat, and here's V. So actually, in this case, this would be the W vector, right? The projection is W, and then V minus W is going to be orthogonal to W, right? So that means that we have picked off all of the components of within W that live in the vector V, and there's nothing else that this vector can contribute from W in order to produce this vector that is the remaining leg. Okay, so in particular, we know just by how we create these orthonormal expansions that this is the complete picture for what W is, right? It's going to be whatever the orthogonal expansion was. You're going to project this guy down onto the W space, and then break up that new vector into the U1 through UK hat vectors. And that can only be done in one way. And you can show that each one of these V minus W inner product UI hat, right? I'm orthogonal to an entire basis of W. Therefore, I am orthogonal to the entire space W. And that's all there is, right? There's all that we can really say. That orthogonal projection is exactly what we get from using these orthogonal expansions that we had from before, or that we've been doing them all along, really. Right? And we're going to go ahead and expand on this next time by trying to collect all vectors that are orthogonal to a particular set into